minute, so get started. So today we will keep talking about background, and hopefully Wednesday we can move to our first attack, buffer overflow. So today we will talk about what are system calls, environment variables. We will spend some time talk about the ELF file format. Also a little bit about the tools we are going to use in this class. Well, so before we get started, there is a homework to ask you to check all the setuid programs in your bin folder. So if you have been trying to find the setuid programs on our server, you would notice that it would be a little bit different from the example I showed you in the class. So in this bin folder, there are still some setuid programs. For example, the SSH-agent, that's a setuid program. However, the S is not appearing in the owner's permissions. Instead, it appears in the groups column. So that is still a setuid program. Just when everyone runs this program, the program's effective UID will not be the UID of the owner. Instead, it will be the UID of the group. Okay, so that's a different example, but still a setuid program. Okay, so let's talk about what are system calls. So system calls are the interface and operating system provides for the process running on top of it. The process or applications, usually they run in the unprivileged level, which means they cannot run some special instructions. They cannot access certain memory regions. However, the OS runs in the privileged level, which means it can do anything it wants to do. So when a user land application or process needs to invoke a kernel service, it invokes a procedure call in the operating system interface using special instructions. And in x86, that special instruction is not the call instruction we saw before. Instead, it's the int instruction. So such a procedure is called a system call. So the system call will change the CPU's state from user mode to kernel mode, and the kernel performance the service, which means the kernel will run some code. Then it will return to the user land. So it's like the process alternates between executing in user space and kernel space. However, when you're executing in kernel space, it is not really running the process's code. It's previously defined the code already in the kernel. So when you write programs, so some of you write C programs. When you write C programs, you do not directly make system calls, but you can. Okay, you can do that, but usually you don't do that. You don't do that. That's because there are C libraries, and those C libraries provide C functions, which usually have the same name as the system calls for you to use. So you call those C functions, and those C functions internally, there will be int instructions to make system calls. But you don't do that. You just make a function call. So those functions are just called the wrapper functions. So on Unix or Unix-like operating systems, like Linux we usually use, there are many system calls, 300, 400. Windows actually have more. So Windows 7 already has like 700 system calls. There are some very powerful system calls, like every program application will use them, like open. It's for open file descriptor. Open, then you can do read, write, close. There are also other system calls to do process management. For example, wait. You can ask one process to wait for other process. EXEC, that's a class of system calls to execute a new program. There is a fork system call to copy a process to just basically make a clone of it. So there will be two copies of the same process. Exit means the process should just quit. There is also kill. Okay, this one is a little bit confusing. If you have never programmed this, kill is basically sending a message to another process. This is a system call to do that. Well, when they designed it at first, probably the only message you can send is to terminate a process. That's why it was called kill. But right now, you can send all kinds of messages to different applications using this system call. Like I said, usually when you program in C, you will not directly make those system calls. Instead, you call C library functions, those ramper functions, and those ramper functions usually have the same name as the system call name. For example, there is a chdir C library function. Ch means change, dir means directory, so change directory. So that is a C library function, but it's also actually a system call. So how you can, if you are not familiar with this, what you can do is get a terminal, you do a man, which is how you get the document or manual of anything in Linux. You do a man, you do a you can, I think you don't have to do two there. You just do this, then you get the document of this API, and in this case, you can say it shows 2, right? 2 means this is a section 2 of the document, which means this is a system call. However, the interface you see here is this is a C interface, so it's not really the interface here is not technically not a system call interface. I will show you later what is a system call interface. This is a C interface. There are other. Let's say we do a BRK. That's another system call. This is a break. This is another system call. If we do BRK3, you can say there is no entry in section 3 because section 3 is for APIs. But if we do this one, no. 4. Okay. This one. Okay, we don't have another entry for this one. Okay. Anyway, so the system call names, usually if there's a ramper, the ramper has the same name. If you, what? Man2? You mean what? Why do I do man2? Oh yeah, I was trying to check if there's another entry in the other section of the document. Yeah. So if you want to say what system calls a program make, you can use a very powerful tool called strace. S obviously is system call. So you trace what the system call program make. You just do a strace. Then you do run the program. Let's say we just run ls. Then you can say all the system calls this program have been making. Okay. So if you took operating system class before, so you probably developed a shell by yourself. So usually what your shell does is take input from the user, then user will give you a program name, right? Then you will make a system call, use exe, cve, or similar names of the library functions. Then you will create a new process. Your shell will fork itself, then load a new program, use the exe, cve. So that's the first system call you can see here. Then the program will use the BRK system call to get where the heap is. BRK can also use to change the size of heap, but when you do not give it an argument, it's just getting the heap. So here we're getting, so that's the return value. So here we execute this program and it's successful, so return 0. Now we have this system call and it gets the address of our heap. Then it changes. So CTR is control, PR here, probably I'm not sure what this one is. So when you don't know what it is, then that's when you can use that, right? So it tells you this one set architecture specific thread state, okay? So you can see that the program tries to set that, but it was not successful. But it doesn't matter, okay? Then it opens another file. It uses a different system call instead of open. It use open at. Those are two different system calls, almost for the same purpose. Just the argument will be a little bit different. Then there is fstat, memory map, close. So this is a system call when you type ls. So what we did, we just type ls. We're trying to list the files in our current folder, and the program makes so many system calls to do that. Okay. If we go to our server, we run any simple program here for the first week's add. We do a asterisk week 1 add. What's the name of that? Asterisk week 1 add. You can see, you remember that add program. That add program only add two numbers together. Okay, it doesn't do anything else. But even that's a very simple program. The simple program also makes so many system calls. First, execute itself, then check the heap, everything else. Also, all kind of memory map. Okay. So if you want to understand a program by running it, you should also use asterisk to figure out not only the system calls it's making, but also the parameters, the arguments for those system calls. So you can get a better idea of what this program does. So on the architecture we are using, most of the system calls, actually all the system calls, relies on an instruction, which is the int instruction, int. And for system calls, we are only using int x80. So x80 is actually an argument for this instruction. So system call is one type of software interrupt. And so you can see the instruction is called interrupt. That's why it's int. However, you can do all kinds of interrupt, but a system call is specific using the x80, which is, what is x80? 128, something like that. For that specific software interrupt. So software interrupt also can be exceptions. And for example, if the CPU is executing something and there is a divided by 0 instruction, and the CPU doesn't know how to handle that, so CPU has to stop executing. The CPU will throw an exception. So those are called exceptions. Also, if the CPU has an instruction to access a memory location, however, it doesn't have the permission to access that memory location, it also generates an exception. So this is a table of the parameters of all the Linux system calls on a 32-bit machine. The 64-bit machine, the system call orders are reordered. I don't know why they reordered, but later in the class, you can see they have different orders. All of this, you don't have to remember. You just need to know how to look for those information when you need to. And also you try to understand how this is designed under the hood. It's not for you to memorize. So here I have a screenshot. Here is a link of all the system calls for 32-bit machine, Linux. And we have 24 system calls here, as you can see. They all have, everyone has a name. Then there is a EAX, means if you want to use this system call, what value you should set in EAX. For example, if you want to make an exit system call, then you should set EAX1. Then in EBX, you don't need anything. One integer here. ECX, EDX, other registers, you don't need to care because this system call doesn't use anything in those registers. If you run to use an open system call, remember, so what does open do? Open will open a file, right? So what kind of parameter you need? At least you need the name of the file. Assuming you already have a file system, you need the name of the file. Also, you probably will need some permissions. You want to read this file, you want to write this file, you want to truncate it, what kind of permission you need, right? So that's why the system call, it also, so if you want to make an open system call, you need to set EAX of 5, then you need to set the address of the file name in EBX. Remember, that's the address of it, so it's just a number. Then you set the permission in ECX. So after you're setting everything up, you just need to make int. You just need to run the execution int x80. That makes the system call. I will show you a more specific example to help you understand how to make a system call in x86. You will write something like this in this class later, but everything you write there is already a template, so it's not that difficult. So on the left-hand side, I have a piece of assembly code. On the right-hand side, I have the ASCII table. Let's say if we can make sense out of this madness here, figure out what is this piece of assembly or disassembly code doing. The first instruction is exclusive OR on EAX itself, okay? So when you exclusive OR on something with itself, obviously the result will be what? Will be 0, right? So what this instruction does is to clear register EAX. So after this instruction, EAX value will be just 0, okay? So then remember, push instruction will push something to the stack, and the stack is determined by the ESP instruction, ESP register, okay? So this will be at the beginning, what does the stack look like? I always draw the high address on the top, low address at the end, okay? So we assume ESP points to somewhere here. So the next instruction will do a push EAX. It's actually push the value of EX, which is 0. So after this instruction, the value here will be 0. So after that, we will push those two crazy numbers, 6873 to FF. Okay, it's a little bit weird what those are. Okay, we will get there later. So after that, we will move ESP to EBX, then do another 2 pushes, move ESP to this, then move, this one is important, move B to AL. Then what is B? A is 10, B is 11, right? B in hex is 11 in decimal. So EAX was 0. After this one, EAX was 0, right? This one doesn't change EAX. This one push it again, but doesn't change EAX. This one changes EAX. AL is part of EAX. Remember that? So we are moving the number 11 to EAX. Now EAX has a number 11. So after that, we make the system call instruction into edit. So if we go back to the table before, we go to check what is 11. Value 11 in EX, we can find, okay, we're trying to execute the system call EXE save E here, okay? Then we look at this, we need some other parameters here, right? So what are we setting up here is this let me see if I have a string here. This is actually a string. The string is slash bin slash sh. So basically, we are making a system call to create a new shell. That's basically what this piece of code does here. This is a system call. The first one, EBX, should be the string's address. And we have the string here. So this is a string. The string's address is obviously in ESP. ESP points to that, right? So that's why we move ESP to EBX. So EBX has the address of the string now, right? Then we push EAX again, so there will be another 0 here. We push EBP again, there will be the address of this here again. Then we move ESP to ECX. So ESP will be pointing to this, and that will be the address of the string again and a 0. Okay, so this is a little bit confusing right now, but you do not need to fully understand this. You will have many more chances to understand this later. But just to remember, so you can see here, this is also a system call. So to use system calls, the instruction is int x80 in hex in Linux. And to use system call, you need to set up corresponding registers. So if you want to know more about system programming, this is a book I recommend you to read. Linux system programming. It teaches you all the C libraries, the Linux libraries, and some of them are just the wrappers of system calls. And some of them are not only wrappers, some of them do much more complicated things using system calls. Okay, the next piece of background is environment and share variables. So in Linux and also Unix-based system environment variables are just a set of dynamic named values. They are stored in the system that are used by applications. And the operating system will place those variables in the application stack when an application is created. An environment variable has a name and also has associated values. The name of the variables are case sensitive. Usually we use uppercase for environment variables. It's not actually required, but we just usually do that. And the name and the value are separated by an equal sign or assignment sign. If you want to assign multiple values to a variable, you will use a column to separate them like this. There is no space between around the equals symbol. Environment variables, you can set it system-wide. They can be inherited by a new process or shells. There are also share variables. Those are variables only applied to current share instance. Share means, for example, the sh you are using, the bash you are using, or I always use zsh. So the share I'm using here is called a zsh. It looks better than the plain bash. There are some common environment variables like user, who is the current user. For example, on my local machine, obviously I am the user, right? So I can do a who am I to show I'm the current user. I can also just get who is the user from the environment variable. I just do an echo $user. So the $sign tells the share that what follows is the name of a variable. So if I do this, it also shows them I'm the user. if you want to find out what programs, which folders of programs we can execute, we can do a echo path. We can say, so when you type any command here, when I type ls, the shell is actually searching a program called ls in all those folders, one by one, until it finds where is ls. For example, we can do which ls. Oh, this one don't work. Anyway, so you can do the same thing in our server. The server, we can do an echo user, and you can say the user is the username is CTF. Okay. So the reason I mentioned about environmental variable here is in one of the challenges we do in the next several weeks, you will put the malicious code or share code inside the environmental variable. There are some commands for you to manage environmental variables. If you do env, you can say all the environmental variables that are set in your environment. So you can see those are so many, those are all the environmental variables. Well, where do we start? Here. Okay. So first is what is the shell we're using, what is the host name, current folder, what is the login name, username, and some environment variable for display configurations. You can also set environment variables just by putting its name and value, or use the set commands. So I'm going to show you this picture again. I showed you this a little bit last week. So this is a memory map of a regular 32-bit program. It's 32-bit program because the memory space is together only 4 GB, right? So the higher 1 GB is reserved for the kernel. Kernel is mapped there. Then the lower 3 GB is for the application to use. So usually we have a stack there, and a stack goes down. Means every time you push, the ESP will decrement. So the environment variable are pushed at the top of the stack when a program is created. So the shell already has some environment variable. And those environment variable, the program needs to access it. The program may have the need to access it, may not. But whatever, the shell doesn't know if the program will need them. So the shell will push those values at the stack so the program can access it. Okay, next we will talk about the format of ELF files. So ELF, executable and linkable format is a standard file format for executable files, object code, shared libraries, even core dumps in Linux systems. They may come with different file extensions, but like I said, in Linux, the file extension doesn't really mean anything. But if you say the file extensions, you get a feeling what those files may be. So AXF usually are embedded system firmware ELF files. Bin is just binary. I do not really say ELF a lot. .o is what you compile C code to a different object file. That's .o. Then KO is kernel object file. Mod is also for kernel modules. SO for shared library. So an ELF file contains the program and also its data. It describes how a program should be loaded. The kernel or the loader will load the program so we can run the program. And obviously in this program, we need all kinds of metadata information to tell the loader how to load it. So ELF files, they all have this kind of format here. So first of all, this is a binary format, and well, everything we have been working on so far, they are L files. LS is an L file. S trace, there's an L file, right? So at the very top, it has a executable header. Then it has program headers, sections, and the section headers. Those are the four main components of an L file. You don't have to, like I said, you don't have to remember those things because in this class, all the exams, all the CTFs, feel free to refer to all the documents. And it doesn't really make sense to remember those things. You just try to understand what they are. So those are the four components. The first one is the header, which is a file header at the beginning of the file. So we have the optional program headers. After that, we have a number of sections. And usually one section also have a section header. As you can see in this figure, the executable header comes first, program header comes next, then section headers. Then the program headers and section header tables, they do not have to be located at any specific location. You can see the section, we draw it in the middle of this thing, even this one. That's because their address is specified in the executable header. So they do not have to reside at a specific location. So here is the data structure of the executable header. So every L file starts with this header. This is a structure of several bytes telling you what is in this file, what kind of L file it is, and how do you find other components of this file. So obviously, we don't need to remember this, but I will show you several fields here so you can get a feeling that what are stored here. We're not going to discuss all the fields, just the several important ones. So the header always starts with 16 bytes of characters. That stores the magic number and other information. So that field is called ident, well, could be identity. So it always starts with 4-byte magic number, which is 7F and the ASCII elf. So like I said, LS is a program. For example, let's use another example. Week one and is a program, right? We do a file. We do a file, week one and it tells us this is a 32-bit L file, right? So since this is an L file, the first 4 bytes, they are always the same. Should be 7F elf. So we can do a cat. Let's do a XSD. Then this one. It shows us the every byte. It's too big. Let's do a head here. Okay. So you can see the first 4 bytes of this file is 7F 45 4C 46. And 45 4C 46, they are just the ASCII of the 3 letters L, right? So every L file starts with this. This is like the magic number. So if you see this, if this file is not malicious, you know this is an L file. The second field we can see here is called E-type. As I already said, L files, yeah. Why it's 16 bytes? Yeah, that's only 4 bytes. The first is 4, right? Then that's 4 characters. Then there are still 12 bytes to store other information. Yeah. What is that? This, yeah, this one is 16 bytes. So all the L files have the magic number, which is 4 bytes. Okay, now, so the magic number is part of this 16 byte, you can say query string or whatever, okay? The magic number is only 4 bytes. Then there are 12 bytes to store other information. Yeah. Then the second one is, this is 16, so it's 2 bytes. So this one tells what kind of L file this is. It could be executable, it could be object file or a kernel object file. Now after that, we have another 2 bytes for the E machine, and this one tells us which platform should this binary execute on. It could be x86 or it could be ARM. There are several predefined numbers for them. I want to introduce you another tool here. It's called readelf. This is also a standard Linux tool. You can do a readelf. We are reading headers here. So we do a weak one. This, then you can say the headers. So this will present us the headers in a human readable way. As you can see here, this is the magic. Then the class is 32-bit. It runs on Linux system, and this one is dynamically linked. The machine is Intel, so it's not ARM, it's Intel. Then there are other locations for other segments in this program. So let's talk about the sections a little bit. So sections are where the code and all kinds of data are stored. There are many standard section types, and also as a developer, you can create your own sections. Because you can create your own sections, the structure of the data in each section could be determined by you, or if it's a predefined section type, then it's defined by its type. The division into sections is intended to provide a convenient organization for use by the linker. So sections are usually passed by other tools, such as binary analysis tools. Some sections contain data that is not needed for execution. For example, there is symbolic and reallocation information in the file to help you debug the program, but not necessarily to run the program. To run the program, you don't need that, but to debug that, the symbols can help you. So for each sections, there is a section header format. Each section first, it has a name. And you can see that the name here is actually a number. So it's an index into another string table somewhere in the file. Then there is a type. What is the type of the section? As you can see here, the type here can be program bits, can be symbol tables, can be string tables, dynamic symbols. Those are the predefined types of sections. And also there are some flags to say what should be the memory permission on this section. It could be writable, it could be executable, something like that. We can also use readelf s to, let me still use this one, to get all the sections. As you can see, I'm still using readelf. Then we can get all the sections in this file. There are, for example, .txt sections. Usually this is where you put the machine instructions of the program. There is RO data section. RO means read only. That's where compiler put the read only data. There is GOT, global offset table data. This is read only data, and this one data is read write data. Then there is uninitialized data like BSS or symbols. So those are different sections. Several flags here. The first one is a write flag, means this section is writable at runtime. Allocate means the content of the section are to be loaded into virtual memory when executing. The exe instruction means this section contains executable instructions. So we go back here. Let's say, well, this one is showing. Let's say, for example, the data one, here we come program. So this program is not showing us the flags. Oh, okay. So the read elf here is not showing us flags. Oh, here are the flags. Okay. Here are the flags. Like I said, for example, this is the machine code section. This is where your code is stored in that elf file. So when you load this section into memory, obviously this section has to be what? Executable, right? CPU is going to execute the instruction here. That's why we have an X flag here, which is executable. And also the loader should create memory space for this section and copy the instructions from the file to the virtual memory. That's why we also have A here, which means allocation. For some of them, let's say read-only data. This section is reserved for read-only data. You're not supposed to write it. You're not supposed to execute anything here. But we still need to copy it to virtual memory. That's why you still have the A flag, but it doesn't have the X flag because you're not going to execute anything here. You're not supposed to. I will talk about several important sections. The first one is Emit. So this is where the L file stores the initialization code. Usually, when you develop something, you develop it in C program, you have a main function, right? The main function will go to, and all other functions, they will go to .txt section. However, your main function has to be called by someone. You probably never thought about that, but your main function has to be called by someone, and that is the standard C library. And that standard C library functions usually goes to the init section. Since there is the init, there is also fill-line means finish. So the code runs after the main program. So also the compiler, the linker, the library will generate those programs. TXT text is where the main code of the program resides, usually where your code, you develop the code will be here. Read only, RO read only stores constant values. You can only read, you're not supposed to change it at runtime. Other values with initialized variables, since they are readable and writable, they will go to the .data section. So this is writable as well. There is another BSS section. It's for uninitialized variables. Okay, this is actually very interesting. When you define a program, you define an integer I, you define int I, but you never initialize it. So after your program is compiled, you got an L file. Since that variable I is never initialized, it doesn't have a default value. When you load the program from a file to memory, does it have to, load anything? Technically, no. There's nothing to load. It doesn't have a default value. So the loader only needs to reserve space for that variable. And by C standard, the loader should initialize everything uninitialized to 0. Okay. But they do not take space in your L file. Your L file only has a name of that. Your L file doesn't really stores all zeros there. And also, because of this design, the loader could be a little bit faster. Uninitialized variables, they do not need to load anything. Go back to our memory map. You can see we have text segment as open, data segment, that's the dot data. Something will go here, the VSS will go here. Heat and the stack obviously are dynamically generated. So there will also be .ro data section, which is not showing in this figure. Another very important concept here, which is very related to security, is we will look at 3 sections for lazy binding. When a binary is loaded into the memory for execution, the dynamic linker performs the last minute relocation. For instance, it resolves references to functions located in a shared library. When you develop a program, you use a lot of C libraries, and the C library doesn't have to be statically linked to your program. So your L file doesn't really have that C library. So your program will use a dynamic linked library, which is shared by all the programs in your system. So the benefit of this is you only have one C library in your memory. You don't have multiple copies. That saves a lot of memory space. However, when your program is loaded into the memory, the program doesn't really know where are the C library functions. For example, where is printf? It doesn't know. So after the program is loaded, the linker, the runtime linker, dynamic linker, or loader need to tell the new program where those functions are. Okay, so that step is called the lazy binding. So in reality, there are a lot of functions in the C library, but your program may not use all of them, right? So when your program is dynamically loaded there, the loader and dynamic linker doesn't have to tell your program where each C library function is, because that's a waste of time. Most of those C library functions your program will never use. So the lazy binding approach is whenever you execute a C library function, then the linker will try to figure out, the dynamic linker try to figure out where is that function and tells your program. So your program use 2 C library functions, the linker will find out those 2 addresses. For other 1,000 C library functions, it never bothered to figure out where they are. Okay, so that is a lazy binding technique. So I'm going to show you a demo later to say how it works. And the lazy binding in Linux is implemented with the help of 2 sections. One is called procedure linkage table, PLT. Another one is called a global offset table, or GOT. PLT is a code section, it's executable. So this section contains entirety of stubs. So basically, it's a very small piece of code to call other code of a well-defined format. Those are dedicated to directing calls from the text section to library locations. And the GOT, there is a GOT dot PLT section, and that is basically a table of the address of other other library functions, and those are filled at runtime by the dynamic linker. So this figure shows how it works. Let's say this is your program. You develop the main program. Your main program calls the say library function puts. Okay. Well, usually you will do printf, but printf after compile actually eventually become puts. Okay. So you call puts here. Then at runtime, when the CPU executor here call puts, it doesn't know where the puts is. So it will actually go to a piece of code which is in a PRT table, and this piece of code will find the address, the puts address in a table, and because it's not resolved yet, it will go to several library functions here to make sure the library will figure out those address, then put the address in the table, then go back here to execute this instruction again to run that. Okay, this is quite complicated. So I'm going to show you a demo how it actually works. So I think you can do this on our server as well, but our server doesn't, we're trying to install some plugins on the server for the GDB. So the GDB were much easier to use, but the TA hasn't done that yet. So I'm going to show you this on my local machine first. It also works on the server, just the GDB on the server doesn't look that good. Let's see. So this is program lazy binding, and you can see the program, a very simple program. It has a main function. The main function calls the same program printf twice. That's it. But you can see that the 2 times we call printf, it will be different. The first time it has to resolve where printf is. The second time it directly calls printf. So let's say if we can debug that. Let me check my. So my make file here. Okay, looks like I should change my make file a little bit. I'm going to add the -G here to add some symbols to make it easier to debug. To make clean, make again. That's weird. So G should be U. Okay, whatever. Let's make it again. So we can do a GDB, the lazy B program. Then we can set a breakpoint at the main. So the reason I want to show you this is also you can get familiar with the commands in GDB. We're going to use GDB a lot in this class. The GDB I'm using, we add a lot of plugins. So we first use B, which is setting breakpoint. We set a breakpoint as a main function. Then we just run the program. And the GDB I'm using will show you all the register values, where the stack is, everything like that. But the GDB we have on the server right now doesn't have those features yet. For example, on the server, we already put the programs in week 2 here. You can see there's a lazy B here as well. If we run this, we do a GDB. Where's the program? Oh, it's week 2. GDB, week 2, lazy B. We still set a breakpoint main. So we run the program. That's what you get. The GDB, this is the vanilla GDB. It doesn't have any plugin. It doesn't basically do not show you anything. If you want to know anything, you have to ask GDB to show you. For example, you want to know what is the value of EX, then you have to do a print EX, something like that. It tells you this is the value. Okay. So if it's not hex, then you can change it to hex. Okay. So it's not very convenient. So the plugin I have on my local computer basically shows you everything. Okay. But it's the same GDB. It doesn't have the fancy plugins. So we are at the main function here, right? So we will use the N instruction means next to debug this. So this is what is the instruction we are going to execute next. Okay. We run this one here. We keep doing until we call this one is not the function to call printf. We look, find where is printf. Okay, this is printf. Okay, so printf eventually compiles into puts. And so this is the first printf. So this is a call. If you do n, you will go to the end of the call. We want to get into that, so we use the instruction called s. This is GDB instruction. Don't get confused with the CPU instruction. Or let me call it command. Okay, we use S to get into the code. Okay, now we get into S. Now we get into. So we are in the GIOIO. Remember this address. Just let's remember this address first. Then let's get it out. So this address is FCD0. Let's now we finish the output. Then we should be able to see the string somewhere. It's already showed maybe. Okay. So the next time we do it, we call it get into the call again. And you see twice we call the same function there, but we're at 2 different addresses. See? This time we're directly at the code section 5655 6060 70. The first time we were at a different address, right? And that's because the lazy binding, the second time, we already know where the function is. The first time it didn't. Okay, let's restart this to say this again. We can run this again. So basically, we'll restart this. Now we are at the beginning of the main function. We do n. This one is one. Okay, those are the two. That's two printf. That's the first proof. Let me do a disassemble here to show you the 2 puts. Okay. Yeah. You can see there are 2 calls to the same function puts at PRT. And the 2 they have exactly the same instruction. Plus 40 and 58. They have exactly the same instruction, but they are going to actually call to different places. Let's say the first one. Oh, this time is already loaded. We have to get out, and this one is already right now is already loaded. We have to do it again here. Bring main. Go run. Do this one. Okay. So this is the first time we call puts. We do S or SI, not really matter in this case. S means a step. It's like in the debugger, you do step by step. But right now we're at the binary level, so it's step instruction. So step is the same as step instruction. But if you have C code here, step will go to the next statement. Okay, so in my case, it doesn't really matter. S and SI, the same thing. Well, they already find the address. Even after, yeah, interesting. Even after I reload this, they already find the address. But you guys see that the first time you got a different address, right? How do they find the address already? How could you remember? Weird. I need to restart a shell. Okay, let me restart a shell. Let me get my shares on. Get a new shell. Okay, this is the first time I call this. Yeah, I have to create a new share for that. Somehow, I should remember that. So the first time I call this, we get to the address F7, which is actually part of the stack. And with this function here, right now we're going to call a function that try to resolve where is the puts function in the C library. Okay. We're not going to debug that, so we just finish. Finish will jump out of the function. Then after that, steer there. Okay, all the way. Oh, I was over here. Okay, I accidentally exit here. Anyway, you can see that the first time and second time going to a different procedure. The second time directly calls the C library function. The first time call into a resolver to resolve the address of the C function. Okay, let's move forward. After talking about the sections, we will investigate a little bit about the segments. So as I mentioned before, the section is mainly for static linking purpose. However, the segment view is used by the operating system and the dynamic linker when they load ELF into process. This sounds a little bit complicated. There are segments, there are sections, but you can remember this. Segments are simply a bunch of sections bundled together. Okay, we can use the L command of read ELF to say the segments. So after I always use executable actually. So we do read ELF L, then which program is so we do an L, then we can say the segments of this program. And the segments are just the combinations of sectors. For example, the segment 5 is a combination of all those sections. A little bit about the tools we are going to use in this class. We are going to use object dump, GDB a lot, but you should also get familiar with other tools. Strings basically print out the readable strings in any file. If you do a string, strings, this program, it shows you all the strings it can find in this program. All kinds of strings. Some of the strings are put there just by compilers, obviously. We are going to use object dump mainly. But you can also choose to use some other advanced tools like IDA Pro. IDA Pro, there is a free version. There's Ghidra. This is a free version, open sourced by NSA. This is a very powerful disassembler or reverse engineering tool, of course. Also, there is a free version of Binary Ninja online. So for most of what we're doing, I would say object dump is good enough. And I want you guys to use simple tools. The simpler the tool is, the more you understand. But I will also show you those powerful tools. For example, Binary Ninja, you can just go to Ninja, just search Binary Ninja. When you find that there's a cloud version, that's a free version. Everyone can use just a register account. I can sign in here. So I've been using this a lot, right? So I load all kinds of binaries there to analyze. So I will just click one of them, maybe this one, and 64, since we have been using this in past. I just click this, and this is a browser-based disassembler reverse engineering tool. And it shows us everything about the program. First is the header, what are the sections, and where the codes are. Let's say if we click here, we get the main code. Do a space bar, we can transfer to the tree control flow view of the program, the main function. This tool is very powerful because it can also lift the assembly to higher level languages. Even to the highest level, it's kind of like C code. So that's the main function. If I do I click this high level IR. IR means intermediate language. If you do a compiler class before, you know what is IL. So if I click that, it will translate the disassembly to C code. So this is almost like C code. Right? Yeah. So this is the main function, and you can say the main function is just to change the value to string, one value to string, then do the main one has three elements, you will print out the image. Otherwise, you will just print out by adding the result of adding those together. So this is not generated by source code. This is the tool generated this C-like code from our disassembly. Okay, but you can see it's quite similar to our C code already. If we do a cat of our original C code, just so this was our C code, okay? Original C code, comparing to binary, then the tool reconstruct the C code from that binary. You can see they are quite similar. We don't have the definition of those anymore. So those are on stack anyway. I think they are optimized already. That's why they're not there. Interesting. See, we actually assigned 0 to A, but the binary code here didn't do that. I never pay attention to this. Let's see if the binary actually assign that to. Looks like it didn't. Oh, what is the add function? Oh, the main function. The main function. Oh, this is the add function. So the main function has two local variables here, A and B. And at a source code level, we actually, at a source code level, we initialize them to 0, right? But after the compiler compile it didn't do that. It didn't initialize it to 0. The compiler optimized that away. The compiler, instead, the compiler generated directly did this, okay? Because the compiler figures out this step is not necessary. You assigned A to something, then immediately you assigned A to something else. So this part is actually bad code. It took this part out. Yeah, look at here. We don't have that. Interesting. Okay, I didn't prepare this part. Yeah. What? Well, that's because the compiler has all kinds of optimization to try to make your code faster, right? And possible program analysis class or comparison. Let me see. If okay. So for that question, there should be let's say, let's use the 32-bit version because this is a 64. It's not directly corresponding. Let's see. How do I get back? Let me create a new session which use file. Let's see, where is it? Code and I don't have a 32 version of this. So the AND one is 32-bit. So it's this one. Okay. So continue. So again, analyzing the program. This is the main function. So you can see here, we have two local variables, A and B. And we add them together. And one of the addresses, right now I cannot quickly tell you which it is. It should be something ESP. Let's see. This one is ESP +4, so this is OXC. Should be ESP minus something somewhere. Okay, so ESP reserve that. So it should be EBP minus something. Looks like even that part is optimized away to a register. Looks like. Yeah, looks like this one is everything's optimized. So I'll save that. Oh, this is a different function. Oh. Which function? Which code is it? So this one, we don't have that initialization. Okay, I cannot find the code here. Oh, anyway, so the initialization basically, the A2 will be a local variable, two local variables, right? So they will be unset. So you will be saying instructions like move, like memory location there. Right. So if you move the value there, let the memory location unset. That will be the initialization. Looks like I have too many copies of those codes. So this one is not. Oh, this is an AND function. This is not the main function. Okay, anyway. Where are we? We have 4 more minutes. So I have some mounts here for you to use later in the class. If you don't know how to use GDB, you can refer back to the slide here. Okay, so the homework issue before this Wednesday. If you have questions, just ping me and the TA on the Slack channel. I do not see many of you there yet. So sometimes some of you ask questions, you send me email. It's much easier for you just to ask on Slack. So other people can see the questions. I don't have to answer the same question multiple times, and also you can discuss with people. Okay, so I think we covered all the basic knowledge. Good. So Wednesday, we will start talking about buffer overflow. That will be our first tech. Cool. See you guys Wednesday. Any questions for the folks online?
No, thank you.